going to take those hypotheses right there and bring them over here and make them numerical. We're going to turn them into using that variable. That variable. Oh, speaking of which, we're saying it's p. Step 2, define the variable in context of what we're testing. We're testing little p, right? What's little p going to be? Close.
Whether or not the vaccine prevented the flu?
How? What is p standing for? What is big? It's a proportion of people that get the flu with the vaccine. That's what we're interested in, right? We are trying to see what the proportion of people that get the flu is once we've shot them with the vaccine. Because we know what the proportion of people with the flu is if we don't get the vaccine. It's what? In the population, little p is 12%, yes? In the population, little p is 12%. But we don't know what the population of vaccinated people's proportion is, do we? Hence the study. That's the whole point. Hence the study. If we can figure out what the vaccinated population's percentage is, then we got something to talk about. Is that fair? Is that fair with you guys? So little p is going to be the proportion, or you know, if you don't want to use the word proportion, just put the flu rate. Flu rate of vaccinated people. Just call it that. Now we only got a sample of 1,000, right? So of course, what are we going to have to account for? Error. Thank you. This is why we're doing a statistical test. We have to account for the error around our estimate, just like we do with confidence intervals. Just like we do with confidence intervals. Totally decent. Fair so far? Decent. Good. Maybe. Ask me that question, Tyler. Oh, you're just taking this in. Gotcha. Now what we're going to do next, thank you for looking at this, is we're going to turn this into step 3. This is step 2, right? Step 2 was making sure we can define that variable, know what it means. Now that we have it defined, let's quantify it. H0, H1, or HA, whatever you want to call it, doesn't matter to me. Either one is fine. I personally like always going with this one first. Just my personal opinion. But you guys can pick either one you want. I'll give you a hint though. They're both going to start with the little p for that proportion. The proportion or the flu rate of vaccinated people. They're both going to start with that. What's going to come next, do you think? What do you think is going to come next? Or what do you think is important about the numerical values in those sentences? What do you think?
Whether or not they're above the 5%.
Oh, you're about 8 steps ahead of me, Ben. Before we get there, in order to, no, what Ben is doing, thank you, if I may draw a picture. If I may draw a picture, what you've done, and I love this, I actually left, if you notice on this template, there's a big blank section directly to the right of your hypotheses. I've left that there intentionally for you if you want to draw a curve in. So, what are we plotting on this curve? In general, what's going to be plotted on this curve? Flu rates. Can I put flu rate? Right, this is the flu rate in the population, the flu rate. If our vaccine is working, where should it be? David's saying left, Brandon's saying left. If our vaccine is working, it should be down here somewhere, right? Good, good. You guys have nice intuition. Excellent. Brandon's 5%. If we're going to throw a 5% up there, what the hell, why not? Yeah? Let's stick with 5% for a while it's comfortable. So if we can land our flu vaccine flu rate here, then we think the vaccine's working. So I want to go back to what Ben said. How do we get in that 5%? What are we comparing our flu rate to? That's what I needed to hear. The 12% in the population is going to be this guy, isn't it? Isn't that going to be 12%? Because that's the average flu rate known from year to year because of studies. Is it always exactly 12%? Of course not. That's why it's got a sampling distribution. That's why it's got a bell curve around it. But the mode, the median, the average is 12%. The question is, are we far enough down to be considered significantly left of that? Is that fair? Good. Now, let's come back over here. Let's come back over here. I think we know what has to go here, don't we? What has to go here, Elizabeth?
Oh, that one's they did not get the flu.
Good.
Given that they got the vaccine.
Oh, I love what you're saying. Oh, Okay, and a statistician's apology right now. A statistician's apology right. You're trying to develop a conditional probability for me and put it right here.
Okay.
The problem with this is, in statistics, there are like 6 different things that have the letter P that stand for them. There is P hat, there is P bar, there is capital P, there is lowercase p. There is lowercase p without parentheses, lowercase. I apologize for all statisticians. This is not the little p outside of those parentheses. This is simply the flu rate of those on the vaccine.
Okay.
What number are we comparing that to?
We need it to be less than 12%.
We need it to be less than 12%. That's all I was looking for. You were awesome for going directly there with it. I thank you for that. We are going to be establishing that right when we get what Ben was talking about, the 5%. We're going to be establishing that conditional probability. Hold tight on that one. Thank you, sister. You're again 7 steps ahead of me. I love that. Now, I want to compare and contrast this with our vaccine prevents the flu. Do you see how this is a more general statement? What does prevent the flu mean to you? You will not get the flu on my vaccine. That's a pretty damn strong statement, isn't it? Because that means if anybody gets the flu, your vaccine's a failure. Do you see how that's going to be next to impossible to do? Of course it is, right? So what's an easier thing to prove?
Fewer people get.
We lower the chances because fewer people get it. Which begs the question, of course, oh, that's a 246 question. That's why, but what's low enough to be significantly low? See how this is just less than? What does less than mean? The quick and easy answer, it varies depending on many factors. All of which we're going to deal with in this example. Bear with me, okay? Okay, we're good so far? I'm getting excited. All right, so what's up here?
That it's greater than?
Or equal to. Yes, so Elizabeth has nailed the trichotomy of these. The trichotomy is that whatever you're testing has to be the opposite of the null hypothesis. So now, just so you know, in research very often nowadays, they simply will put an equal sign. Just so you know. As a mathematician, that pisses me off. As a mathematician, I want exactly the opposite of this. Because I want to account for the possibility that I give you a flu vaccine and you get sicker. I want to make sure I've at least symbolically controlled for that. The test will control for it. You can see where the greater than part of this curve is, right? It's over here. What if the flu rate is 12%, I inject you and now you've got a 25% chance of getting the flu? Well, we stop making it, obviously. We start putting in biological weapons, maybe. But the idea is that we've now accounted for that in the hypotheses. That's why I like it like this. You might see a lot of equal signs in the research. Just so you know, FYI, FYI. Is that fair? Believable. You guys buy this? Ask me questions if you have them. Not a whole lot of math yet, I promise. Math's coming, math's coming. But first, before we go any further, let's talk about the types of error. What would a type 1 error be when this test is over?
You say that the vaccine worked when it really didn't.
We say that the vaccine works, but it actually doesn't. See when that's a type 1 error? It's a false positive, right? A type 1 error is a false positive. That means you falsely believe this. You falsely believe this. Think type 1, H1. You falsely believe H1, yeah? So you say that the vaccine is working, when in fact, the vaccine is not working. That's a type 1 error. In context. In context. Fair enough? Say that the vaccine is working, when it's actually not working. The pharmaceutical company loves this, of course, because it means they're going to sell a product. Of course, the problem is they're selling sugar water, essentially, for flu vaccines. Good? Type 2 error. Type 2 error. That's your false negative. In context, that means say that the vaccine doesn't work,
And it did.
but it actually does, and you missed it. And you missed it. So looking at your curve, a false positive would mean that you landed out here in Brandon's 5% region, but it was just a goofy random shake of the dice. You should have actually landed back here. That's a false positive. A false negative means you landed in here, but that was actually an outlier on a curve that was actually way down here. See the difference? Now, number 5 here, I think. Which type of error is worse in your opinion?
Type 1.
Vote for type 1, Connor! Why? Tell me why.
Because if we say it's making you better and you actually got the flu, that's pretty bad.
So we're actually distributing a product that is doing nothing in the environment, and somebody's getting paid a lot of money, maybe even state funded through your tax dollars to do so. Good, I love that. Who else says type 1? Excellent! Who says type 2? Tell me why, Jake!
Because if it is effective and we say it's not, then it could have helped out a lot of people.
They're not going to mass produce it. If they say it's not effective but it actually is, they're not going to mass produce something. Do you see how both those points are totally valid? Do you see now why statistics is so loaded with gray? You have to now decide which one of those you would want to avoid more as a statistician. Jake, if you want to avoid a type 2 error, you have to accept more of a type 1 error, which means you're going to have to take this and move it where? This way. That's your type, that red area is your type 1 error. Right now it's at 5%, yes? You're going to have to make that bigger than 5% to reduce your type 2. You might not know why right now. That's okay. That's why I have a project coming for it. This whole idea of moving one to decrease the other. Connor, if you don't want a type 1, you shrink this down. You shrink this down. Make it as small as you possibly can. That blows up the chance of a type 2, but if you can live with a type 2, that's okay. It's all about what can you live with the least / most. Is that fair? It's full of gray. It's full of gray. There are no foregone conclusions in this class. Sorry. Yeah. Cool? All right, how are we doing on time? We have a little bit of time. Let's see if we can crunch this test statistic. Which distribution should we use? Any ideas? We've only talked about 2 so far. We've only talked about Z and T. We're going to use Z, aren't we? How come? Because it's a proportion, we have a discrete sampling of 1,000, and we have measured 101 of those 1,000 to have a characteristic. Thank you. Z distribution. Yes. Yes. Now, the question I have next is, we're finally going to firm this thing up. We're finally going to firm this thing up. Flu rate. So we've drawn this curve up here. And we're happy, I think, with this curve. It's time now to figure out where our data landed on this curve. Because if our data lands here, what do we tell the pharmaceutical company? What do we tell them?
It's not worth it.
It's not worth it. Go back to the drawing board and try again. If we're basing all this on one test. If they land in here, then go back and finish. If they land over here, possibility it's working. Lands over here, call the Pentagon. Probably got a contract for you. But if they land over here, it's working. If they land here, it's not. My question is this. What value is right there that breaks off that from that? Now, your TI won't do this for you. Because how many of you are thinking confidence intervals? Let's make a confidence interval around it. Was anybody thinking that from the beginning? Yeah, the problem is your TI only makes what are called two-sided intervals, which would then put 2.5 and 2.5 and go like that. It doesn't make a one-sided interval. And that's okay. We could make it do a one-sided interval. I just don't want to because if you're interested in what a one-sided interval looks like, if you go to the extra resources for hypothesis testing, I've got a big long E problem in there that describes it for you. If you want, you can also not worry about it at all. But there's a mathematical way of figuring out what that has to be. And it has to do with normalization. When you were in 243, any bell curve could be normalized so that what number was in the middle? Do you remember this? It's been weeks, if not months, that you studied this. And mu for the standard normal was what numerical value? You don't remember, it's totally fine. It was 0. We could make z-scores be centered at 0. It's been months for you guys that had me in 243 last term, literally months. You could take any bell curve and re-normalize them down using a z-score computation. This is the first computation. Z-score, remember z-scores? It's okay if you don't. It's okay if you don't. It's totally fine if you don't. But a z-score from 243, a z-score was a way of taking a raw data value and normalizing it with a known mean and a known sigma. And then out pops a number that's centered on 0 and goes positive 1, 2, 3, negative 1, 2, 3. It's been a long time since we actually crunched this. You crunched them when we did single proportion confidence intervals too. It's been 3 weeks since then. Fair? All we need to do now is to take 244 and do the exact same thing. Now I want you to look at these 3 pieces. I might hold the computation until Tuesday. Yeah. Let's just get the general idea of what a test statistic is going to be. Because I call this a z-score. Sometimes it's going to be a t-score. Sometimes it's going to be a chi-squared. Sometimes it's going to be an f-score, depending on what we're talking about. We'll get into all those later on in the course. So what they all are, though, they are test statistics. We'll hold the actual computation for Tuesday. But basically, what it's going to be is this echoed for inferential statistics. So where you see x, what you're going to put in for x is going to be the sample statistic. What's that going to be for our test right here? Just do a conversation. We'll do it in numeric numbers on Tuesday. What would our sample statistic be from this? The flu rate in the sample,
101.
which is 101 out of 1,000, 0.10110.1%. That's going to be what we're going to put there in the formula when we crunch on Tuesday. So just a heads up, p hat. We used to call it p hat. Remember that little guy? P hat. Yeah, he's coming back. Hi. We are then going to subtract from him the assumed population parameter. The statistician's apology again, Elizabeth. Once again, because when it's x minus mu, it's like, whatever, I can totally tell those are different. What's the population parameter in our study? 12%, which we call little p, right? Little p by himself is 12%. Now, who is going to say to me that 10.1% and 12% are pretty close to each other? Who's going to say they're pretty close? Jake says they're pretty close. They're less than 2% difference, less than 2% difference. Honest, yes, pretty close, pretty close. Contest that. Because what does close mean, right? What does close mean? What measures closeness in statistics? The margin of error. And that's what goes down here. You have to metric the closeness with the standard error gotten from the study. Close doesn't mean anything. Close doesn't mean anything unless you can metric it with the error from the sample itself. The computation for that will hold till Tuesday, because I don't think we have enough time to actually get into it without making you all projectile vomit. But we'll get to that too, I promise. Everything you need is right there in those two sentences. We can do this. We know that's 10.1%, that's 12%, and this is a function of all those things in the 1,000. And we'll get to it on Tuesday. Cool? You will have an exam grade for me, hopefully before the end of the day. I'm going to knock out your guys' exams next. Answer that question, Aaron. Answer that question. You're processing, I can tell.
I want to know.
Oh, you already do. You already do. Check it out. Ready? This is 10.1%, 0.101. Fair?
Yes.
0.101, 0.12. This guy here, square root. Yes, remember him? P times Q over N. Boom, done. There's no Z multiplier because that's actually going to be over here. But this is a confidence interval just solved for a different value. This is your Z-score. That's your standard error. That's your assumed population parameter. There's your standard. It's X bar plus or minus the standard error times his confidence value. But it's all wrapped up and solved for a different variable.
So if you put it in the calculator as a t-test?
Yes. It does it for you. Because the standard error is guaranteed from the 101 and the 1,000. Yeah. Once you know that P hat is 10.1%, you know that Q hat is 89.9%. And P hat times Q hat over N with the square root is the standard error. It's the binomial standard error. You don't sound convinced, then that's okay. Here, do this with me. Don't even worry about this. Don't worry about this. We'll get that out. No, get out of here. Get out of here. 0.101 times 0.899. Thank you.
You're welcome.
Enter. Divide by 1,000. Okay, enter. Square root, second square. Second, actually, second, you would just go, do second square root, so second x squared, then second negative sign. Enter. That is your standard error. That's what goes in the bottom. 0.9%. very tight standard error, right? That means the margin of error is about 2%. If you multiply that by 2, you get 2 standard deviations, 2%. That's a very small margin of error. Your sample's 1,000, pretty big, and your proportion's pretty small, which also drives it down. See, your question is great. What's the standard error? It's all based on your sample size and how many of those people in the sample size got the result. Does that make sense?
Yeah.
Ish.
Why can't you use the one prop?
Oh, you can. You can. If one prop z int would do a one-sided interval form. See, the problem is, watch. That's the problem. We need a one-sided interval because we need to know just what that number is right there. We don't want this and this. We only want the one-sided tests to be done. So you can, it just doesn't give you the equivalent results. Why? Because TI never gave us that option. I don't know why. What in Sean's world, you'd have a one prop z int, and then the next choice would go one or two sides. And if you chose 2, you would do it like normal. And if you chose 1, you'd say, which side, left or right? And then you wouldn't even have to teach hypothesis testing, because everything would be confidence intervals. You hear in this YouTube world? Pay attention to me. But nobody does it that way. It's unfortunate, because they would be equivalent results if you did it that way. More to come. 5 more weeks. More to come. I promise. I promise more. I promise. Jake!
When will you be in your office this afternoon?
I have no idea.